Okay, welcome back to the Neuro Symbolic Channel. I'm here with Hikaru Shindo and Quentin Delfosse.
Yeah.
Okay, well, nice. Good, I got that right.
Yeah.
Nice to meet you both.
Yeah.
So,
Nice to meet you.
Quentin and Hikaru are both out of TU Darmstadt. They've been doing some really great work at the intersection of inductive logic programming and reinforcement learning using neurosymbolic approaches. I think it's found it really interesting. I actually first got introduced to Hikaru's work with a AAAI paper a couple years back about differentiable inductive logic programming with functional symbols. We actually did a little video series on that a few months ago, so I'll link that in the description. But, really glad you guys could make the call today. Maybe if you could start out by just saying, how you got into the field, what you're doing now, why you're at Darmstadt and stuff like that.
Hiki can
Okay.
start, I guess.
Yeah. Okay. Cool. So thank you for having me today. I'm Hikaru Shindo. I'm PhD student working for TU Darmstadt with postdoc Quentin casting. And I'm mainly working on, in general, neurosymbolic approaches, mostly trying to integrate parser logic, making parser logic differentiable and try to integrate with neural networks so that we can solve many practical problems and perform problem solving beyond just perception by neural network. The reason why I got to this field is the first I worked on the pure symbolic ILP work on my bachelor thesis, symbolic programming induction. Then I found it's neat. I mean, it's a cool work that apparently it has different features. I mean, advantages against neural networks. But compared to neural networks, I also found that kind of drawback, like in a sense that it requires a lot of efforts to tackle practical problems in real world. For example, we need to process raw data, images, whatever, in a noisy world. So for me, that was very natural to come up with the idea of neurosymbolic computation that tried to have neural network to process such a noisy data and also combining symbolic abstraction, representation, and reasoning so that computers, we can have a computer that perform reasoning, not only perception. And in the end, to this end, we worked on differentiable inductive logic programming, trying to perform program induction, symbolic program induction by using gradients, just like we do with neural networks, towards the kind of the very well integrated neurosymbolic system that performs reasoning and learning together with neural networks. And as you mentioned, yeah, I worked on the differentiable ILP on 2021 or so, and after that I came to Darmstadt to pursue my PhD, and I met many colleagues, including Quentin there, who is working mainly on reinforcement learning, and we combined our approaches to establish new neurosymbolic system. So for me, this work was a kind of the very first practical application of the differentiable logic, what we have been working for long years. And yeah, that was pretty nice experience that we are getting out that something actually working. We are using symbolic reasoning, but it actually solves very practical and interesting problem of reinforcement learning. Yeah, that's for me. Thank you.
Oh, I think, that's really a fair point. Like, a couple months ago, with some colleagues, we gave a tutorial on neurosymbolic AI at AAAI, and just talking to people toward the end of that event, there was multiple people had came to me and told me, it's like, we need to identify the ImageNet problem for neurosymbolic AI. We kind of need that practical problem to get people to pay attention and push the field forward. So, I really appreciate you saying that about real world problems. Quentin?
Yes. So hi. So I'm Quentin, as you said. I studied most of my curriculum in France before I came to Darmstadt and met Hikaru. So for the small story, we're roommates actually. So that's a roommate paper that we have. And I'm coming more from the reinforcement learning side. So I've always been like fascinated with robots, C3PO stuff when I was young. And so when deep reinforcement learning started solving chess and then Atari games, I was all amazed. And when deep learning was starting solving computer vision, speech recognition, etc., I came more from the practical side. And I have to admit that at the beginning, I was not that much into neurosymbolic until at some point, I found a channel of Robert Miles on YouTube, who is speaking about safe AI. And he really well show how if you don't use any neurosymbolic approach or any interpretable approach, you are really not safe. You're going to have agents that you've trained through reinforcement learning that are really likely to learn misbehavior, misalign with the ultimate goal you want to have. And this is where I started understanding that we need neurosymbolic AI if we want to be sure about what the AI agents and the robots ultimately are going to do and how they reason actually. Because I used to be part of this crowd, so to say, that thinks that deep learning is enough. And but I came to realize that was not the case, and now I really need that I really think that we need to integrate neurosymbolic reasoning in order to be sure about the behavior of our agents. And the more it goes, I mean, on the paper that we have with the nudge framework that we've developed with Hikaru, we try to show that also that you have many advantages. But lately, I also came to realize that I'm going to need, or we are going to need neurosymbolic even more than what I thought at the time of writing with Hikaru, because I've detected lately misalignment problem in Pong, which is really a simple game. And so, yeah, that's where I realized neurosymbolic has to be part of the game here.
Maybe you touch on that a little further about the misalignment problem. That sounds interesting.
So the misalignment problem is actually a problem. Would you like me to share my screen maybe?
Yeah, sure.
Because, okay, I actually had to prepare a bit of a talk on that lately. And so like the misalignment problem that Robert Miles is explaining is this problem that in reinforcement learning, you try to get a policy to learn the correct behavior. And so in this game here, you're trying to have an agent that learn to go to the coin. The game is called Coin Run. And so the goal is to go to the coin that is usually placed at the end of the level, because they generate the level on the fly when they train the agent, and they place the goal at the end of the level. There is no point generating the rest of the level after that, because that's supposed to be the end goal. And if you look at heat maps, so deep techniques and deep explainability technique that are not neurosymbolic on a deep reinforcement learning agents, what you're going to see is that you have positive attribution on the coin and negative attribution on the enemies. So that's going to reinforce the human, or that's going to really emphasize their thinking that the agent is well aligned, actually, that it understood that the coin was the goal, that was the positive attribution, and so that it had to reach for the coin. The thing is that later on, what it was discovered that if you randomize the position of the goal on agent that have learned through deep reinforcement learning, the agent actually doesn't catch the coin all the time. He sometimes passes the coin and go till the end of the level. And the idea here is that you have a correlation, a misalignment possibility, because the coin is always placed at the end of the level. And for such an agent, it's easier to learn the behavior to go at the end of the level rather than running to go to the coin. But if you don't have a reasoning agent with neurosymbolic system, you cannot actually detect that it doesn't really care about the coin. It knows that the coin is actually important in order to get positive reward. And when it's going to pass the coin, it's going to still tell you, oh, I'm expecting positive reward, but it's not going to go get it. And lately, while I was working on neurosymbolic approach to solve the game Pong, I discovered that you have actually the same problem in Pong here. If you look at this agent playing Pong, it's going to basically it's going to win the game 21-0 or 21-1. So the green paddle is actually the agent. And if you look at heat map, what you're going to see is that, and this is results that I've reproduced here. I was reproducing that this morning. The agents are actually really paying attention to their own paddle, the ball, and the enemy paddle. And so what you might think is that there is no problem. Like it understood that it has to throw the ball behind the enemy's paddle in order to score, which is ultimately what you're going to want to optimize for. And there is supposed to be no problem. The thing is that if I go back to this animation, what you're going to see is that the position of the enemy paddle is always aligned to the position of the ball. And so you have a correlation between the vertical position of the enemy paddle and the position of the ball. So you have a misalignment opportunity here. And obviously our stochastic machines that don't use symbol to reason, they fall into this trap. And so now if I take the same agent that you saw playing up there, and I let it play on the original environment, this is what I obtain at the score. If I had the enemy, which for a human shouldn't make any difference because you just still supposed to make very bumpy shots in order to win. But here, because it was aligned on also looking into the position of the enemy, it's not going to be able to perform well. And so it's not scoring anymore. And so this shows that even in the simplest game that is Pong, you have a misalignment opportunity that people have not really found beforehand. I mean, maybe they were not looking for that, but for me, that shows really that these misalignment opportunities are pretty much everywhere. And that if we don't have neurosymbolic reasoning that Hikaru's framework, among others, allows to nicely have, we cannot really interpret why the agent is taking any decision. And in the real world, I think the misalignment opportunity grows exponentially. And so, yeah, that's why I'm leaning towards like having neurosymbolic logic reasoning inside our deep learning agents.
No, that's interesting. I mean, to me, that strikes me as similar to problems observed in perception, like the example where a Siberian husky is recognized, but it turns out the model's really recognizing snow and stuff like that.
Yeah. Yes. That's pretty much the same. So it's easier to categorize CT and snow or forest and urban environments rather than a wolf or a dog, basically. And so you're having this shortcut learning, basically. And in reinforcement learning, this shortcut learning has been several times called like misalignment, because the policy learn a goal that is misaligned because it's aligned temporally with the goal you ultimately want to optimize for, but you're not sure that it's always going to be aligned for this goal. And yeah, so learning with reinforcement learning so that's why we wanted to show that using heat maps is not enough. Even if using heat maps give you good intuition on what is the agent processing, what is important. And we're going to show that in the paper also, that you have this differentiability, which allows you to have explainability, but that's not enough. And I think naturally in neurosymbolic approach, they give you this interpretability, that you really understand how the signal is being processed and what is the intention behind the decision that is taken.
No, I think that makes a lot of sense. I think that the other thing that it gives you beyond that with any kind of symbolic result is the ability to do further computational manipulation on that result, where I think a lot of this, these kind of XAI explainable ML techniques that don't use logic, is just kind of providing some of the things you were showing there, like heat maps and stuff like that. And it's okay for like diagnosis, but you can't really do anything further computationally.
Yes.
Yeah. In our paper, actually, we have shown that we took the similar technique. I mean, computing the gradients to get the heat maps, but we casted that gradients on top of the logic. I mean, top of the symbolic representations, and that's our system somehow can explain the reason why this action has been taken because of blah blah blah. I mean, computing the heat map, but it not casted on the image itself. It casted on symbolic representations, and it has better interpretability and also explainability compared to the other. I mean, deep, purely neural-based agents. I think that's pretty cool advantage. I mean, gradient computation is a kind of neural technique which has been developed and integrated with neural networks. But we also have now logic. I mean, we maintain the differentiability of the reasoner, but also we also have an explicit symbolic representation. We can play a game there. I mean, we can take the best of both worlds to produce such explanations using symbolic representation, but it's flexible enough that can work on a very noisy environment like reinforcement learning out of the symbolic environment. That's a very cool part of the Neuro Symbolic agent. Yeah.
Well, I mean, on that note, why don't we get into the paper a little bit? Let's let's introduce that.
Yeah. So we prepared a slide and we can share. I can. We also have a bit of demonstration, and let me share.
All right. So let's get into that.
The explanation stuff first. You mean? So
wherever you want to start. Why don't you start from the beginning? Because
okay.
We've all read the paper, and my audience is gonna start to get lost, I think. So.
Oh yeah. I mean, we prepare slides, removing like very macro technical details to give the overview, so it should be fine. So this work is about the paper title is an interpretable and explainable logical policies via neurally guided symbolic abstractions that we are aiming to establish reinforcement learning agents that are interpretable and explainable by combining differentiable logic, reasoning, and learning on top of the reinforcement learning themes. So we are tackling here in reinforcement learning. That means the goal is to find an optimal policy of the agents. So in a reinforcement learning, we have basic components of agent and environment, and basically agent observe the state and decide an action by interacting with the environment. Like this is an example of Pac-Man, and Pac-Man decides action, go up and left and so on. Then environment then interact with the environment, that then the environment returns the reward and state, and agents can know the next state and also how good was the action. And the task is to maximize the cumulative reward. That means performs better and better by trial and errors, by making trial and errors by interacting with the environment. And the deep neural networks are the mainstream to implement the actors, that means the agents in reinforcement learning. But as we know, deep neural networks are often claimed that they are black box, that it is difficult to explain the decisions. It is not easy to interpret what they have learned actually. And also it is the agents with purely neurally implemented are not robust to environmental changes. That means, as Quentin mentioned, like if we change a bit of the environment, then they are likely to fail to adapt themselves to the new environment without additional training and whatever. And we believe symbolic reasoning can help, but it is not easy to integrate purely symbolic system in the middle of reinforcement learning system, because reinforcement learning use these kind of policy gradient approaches. Basically means they use gradients heavily to train neural networks. And if we put symbolic system in the middle, we can break that learning system. And also the search space of symbolic learners is kind of exponentially complex. So the question is like, how do we learn efficiently using symbols, and how to integrate non-differentiable reasoning system with reinforcement learning schemes? So we focused on this work to work on actor-critic framework. So basically, the agent has two basic components of actor and critic. Actor decides action. Given actor decides action, then critic evaluates the actors. And our basic idea is replace this neural network for actor with the differentiable logic reasoner we have been developing for other previous work. So this is a kind of overview of our framework. We propose neurally guided symbolic policy. We name it as nudge, and nudge takes an input state as a, like we can feed like image, for example, and we can perform object detection, whatever, then we obtain this kind of relational representation of that state. For example, this game is about Get Out. That the task is for the agent is to get the key, but avoiding enemies and reach a door. This state can be converted to the set of probabilistic atoms in first order logic. That means object 1 is an agent with a probability 0.98 and so on. Object 2 is an enemy, and the agent in this state agent doesn't have key and so on. And given this state, and also using weighted logical rules that describe action, our agent produces action distribution by performing differentiable forward reasoning here. So action in our framework, action are defined by the set of weighted rules. So we can read out for the first rule, for example, if object 1 is an agent, and if object 2 is a key, and the agent doesn't have the key yet, and the key is located on the right of the agent, then the agent should go right, apparently to get the key like this. So in this situation, if you play this game, you likely to go to right because you don't have the key yet, and you also want to go to the door. And in our framework, after having this action, we can ask to the agent, why did you take the action and go right? Then by having the XAI gradient-based XAI methods and cast them on the logical representation, our system can produce a kind of explanation using logical representation. So in this case, the agent can produce the explanation because the agent doesn't have the key yet, and the key is on right of the agent. That's why we should take the action of right in this situation. And we established a kind of policy reasoning and the policy learning framework using differentiable logic reasoning. So first, I'm going to briefly explain how do we do policy reasoning. So input, as I mentioned, the input state is going to be converted to the relational representation in a form of atoms in a first order logic. So input state, given input state, we get a set of bunch of probabilistic atoms that describe this state, basically. And next, we perform reasoning, forward reasoning, to produce the action distribution. So as I mentioned, each action is defined by the set of weighted rules given atoms that describe state that derives action. In this rule defines go right action. This rule also defines go right action, but with a slightly different reason. And also the third rule defines the action of jump, because if agent and enemy are getting close to each other, the agent should jump, this rule tells you. And we compose the policy. I mean, the policy is a function that produces action distribution. We compose this policy as a set of weighted rules, and by using these weighted rules and given logical representation of the input state, we induce the action, the probability over actions. And using this information, we produce the final action distribution. In this case, most probably the agent will take right as an action in this situation.
In the induced actions,
yes,
those numbers by the atoms, are those actual probabilities, or are those fuzzy values?
Actually, it's more like fuzzy values.
Okay.
It's not, as you see, it's not normalized yet. Like jump can have this value, but right can also have values. And we normalize using these values, these fuzzy values, we normalize to have a valid action distribution. That means this normalized distribution over actual actions. I mean, yeah.
Yeah, I get that. I guess the other question I have though is, so right 1 and right 2, those are the same atoms.
Yes.
Just rule 1.
Yes.
Okay. And then
yes, exactly. So the reason why we explicitly distinguish is these two predicates of right 1 and right 2 is we can encode different reasons to take an action. So in this environment, when you want to go right, actually you can have several reasons. I mean, before the agent gets key, the reason should be like go right to get the key. After having key, the reason should be like to go to the door. I mean, in this situation. So yeah, of course we can use the same predicate to describe right, but in our work, we distinguish. I mean, we prepared two different. In this case, we prepared two different predicates to define one action, to encode the different reasons for the same action explicitly. And by doing so, as we have shown in experiments, this leads to more clear explanation of the reason for the action to be taken. Why did you take right? We can ask the agent, and the agent can clearly explain the reason of the action, because we don't have a key, and the key is right side of me, and that's why we should take right, for example. That's why, yeah.
So the other thing with that is in your rules, there's fuzzy values in the head.
Yes. Not
in the body, yet your logical state representation is fuzzy values. So how are those combined?
So each rule performs reasoning, yeah. So this rule performs forward reasoning. So if all of the body atoms have high values, fuzzy values, that will deduce this atom with a high value, right? If this is almost 1, this is almost 1, this is almost 1, this is almost 1, then we get almost 1 for this atom. But if this weight is also high, so in the end we get almost 1 value for this atom in this case. But if this weight is very small, even though this rule deduces I mean, this atom with high value, but it's gonna be it's gonna be very small value in the end. And we need these values. The reason we provide these values is like we perform learning on policies. I mean, we want to learn which rule is actually promising to compose policy function for the reinforcement learning agent. So we listed only, I mean, good rules here, but in practical cases, we have a bunch of redundant rules. And by having weights and optimized weights, we can somehow prune the redundant rules and like pick up some very promising rules to compose logic policies. And yeah, that's why we have weight for rules and also kind of fuzzy values on logical atoms. And we consider both of them. And these values are integrated together in a reasoning process denoted as 2 here.
Okay.
Mm-hmm.
So maybe if I can give a more high level, because Hikaru is
maybe that was yeah.
And so on the high level, what you want to have is a set of rules that describe a reason for different action, but you might have different reason for the same action. So you might want to go right. For example, there is an environment that we're going to show you where you might want to dodge an enemy that is coming, and you might want to go to the goal at the same time. But you might have like 2 possibilities to dodge. You might dodge by going down if the enemy is coming from the right side, or you might dodge by going up. And the most sensible thing to do if your bonus is on top is not to dodge going down, but it's to dodge going up, sorry. And so this is why you have different rules for one action, and then you have to combine those values. So this is what you see in the induced action atoms. We have different values for the different rules that we obtain. Also, there are 2 problems at hand here. The first one is to find sensible rules on which Hikaru is going to come. And then it's to order which rule is more important than the other. Because it might be that sometimes in some situation, all of the elements that compose these rules have very high value, but it might be a more important thing to do to jump than going right when the enemy is coming towards you. So here, in this environment, the agent is going to die if he doesn't jump when the enemy is coming. And so jump might be actually a more sensible thing to do. And so this is why we have to give weights also to the rule to know how to order them. And this is basically about like policy learning. Yeah. If I give you a set of like possible action and reason why, you might want to know which one is more prominent, more important than the other. And so this is why you have weights on the rules. You could also learn that way, like generate every possible rule that you could do by composing those atoms together, and then just learn the weights of these rules. And hopefully, because we have something that is differentiable, what you could have if you wouldn't generate infinitely many rules, would be that you would learn that stupid rules would get or non-sensitive, not optimal rules would get a very low weight, and the optimal rules that lead to the optimal policy would get a high weight, basically.
No, thanks for that. And I mean, I'm already starting to see as you say that, going through all the possible rules and assigning weights, it already starts making me think of the inductive logic programming stuff. But I guess it's where you're going pretty soon here, huh?
Yeah.
So the problem is like how to generate this kind of set of rules, which are going to be assigned. The weights are going to be assigned with. So in our framework, we obtained these rules by kind of performing symbolic abstraction on top of the pre-trained neural agent. So we assume pre-trained neural policy, that is just neural network, works pretty well on the environment. then we perform like symbolic abstraction on top of that. So I wouldn't go to the very detail, but intuitively, we have neural policy. This represents S is a given state, observed state, and this function produces distribution of actions. This action should be taken, for example. And we also have logic policy, and we compute the similarity between these, and we evaluate each rule by computing the similarity between the well-trained neural agent and the action distribution, which is produced by the rule. So intuitively, we've like good action rules, good rules defining action should produce similar action distributions as a good pre-trained, well-playing neural policy. So simply we just take dot product and normalizing and so on, evaluate each rule, which rule looks better than others to compose policy functions in the actor. So we call this as a neurally guided symbolic abstraction because we guide the search of logic rules using neural network. So this works pretty efficiently. I mean, as we discussed, like the very naive ways is to generate possible rules by combining, I mean, as a combination, just enumerate all the combinations of symbols. But if you dive into practical problem with many possibilities, options, this approach is not going to work anymore because I mean, exponentially, it's going to be difficult to solve. So we just choose good rules by guiding using pre-trained neural agent, and now we have a bunch of rules that define actions, but we don't know which action rules are actually good. So, and in the second,
actually go back one. I
Yeah.
actually had a quick question or maybe comment. So if I understand right, the neural policy is operating on the same state space as what you showed in the previous slide, which is symbolic. And so so what are your thoughts on how these kind of ideas would adapt to a continuous space where where a neural approach would be like something like in the Atari games where the lower levels would be like a convolutional net? Would you kind of look to have sort of a frozen series of convolutional layers just to recognize what's going on and then reason on top of that? Like kind of what's your thoughts on that? I know it's beyond this paper, so
your idea is to freeze the neural network to observe.
So I guess what I'm saying is what are your thoughts on this approach is designed to work on a
continuous
symbolic kind of space. So when in adapting to a continuous space where you want the agent to just perceive what's going on, how would you adjust to that in future work, you think?
Actually, yes, that's a good question, because I mean, logic is dedicated to encode discrete states. Even, I mean, the one workaround, I would say workaround approach is cast such continuous information to the fuzzy values. I mean, we have discrete logic representations, but numerical value is associated to the, we also have numerical values over atoms. So maybe we can encode the continuous knowledge, I mean, continuous values by casting the numeric values to the atoms. I mean, this is pretty workaround approach, but when it comes to deal with the continuous actions like lever stuff, I forgot the actual name. That should be pretty challenging task for the Neuro Symbolic approach. I mean, to represent numeric values, we need the infinite number of symbols. And
can I also add something on that, Hiki?
of course, I mean, yeah.
Because that goes a bit back again on the how would you integrate like the deep part of that, and we have actually worked on that. So, Hiki, if that's fine, I would share a bit, and then we go back to the following, because the question is like it would be a bit unfair to compare that to a very deep learner that is learning from the raw pixel input, if I understood correctly.
Yeah, that's what I was getting at.
Oh, okay.
And okay, if I'm able to I'm going to try to share here this one here. So like we actually have something on that that I was working on that we're going to present at ECML soon. And so this is the how do you detect object actually and go from this deep state into, like as you said in Atari games, into a neurosymbolic method. And so what we did with another colleague from TU Darmstadt is that we took different object detection and supervised object detection method, namely two space and slot attention. And what we had was we tried to use these object detection method in order to detect the objects without any kind of supervision. And at the beginning, I wanted directly to use that in order to integrate into a deep reinforcement learning framework and have like Neurosymbolic already integrated. Problem is that when I tested, the only framework that was developed for Atari games was space, not slot attention at the time. And when I tested, it was really bad. So you can see here the F-score is actually, 60% is already not good enough to play a game. Yeah, if 60% of the time you detect object, or if you detect 60% of the object, it's not going to be enough for you to have a successful policy. So like the only game that we could tackle using space was Space Invaders that had a reasonable object detection score. But then when you looked at the internal object representation that it had, it was very, very bad. And the gist of this paper was to try to use time in order to bring consistency and in order to improve the object discovery performances. And so this is another paper. So this is more on like, how do you detect objects, etc. So that's a bit outside of the scope, but we showed that by using very, very simple optical flow, we were able to detect objects in both methods. We were able to boost the performances of our space baseline and the slot attention baseline. And we're able, like, using this method, we're able to learn faster. We are able to learn to have better detections, and also we are able to have better mutual information. So we're able to easily classify objects after we've discovered them, because we use a contrastive loss basically to distinguish between the different object types that you have. And so this is something that we then try to integrate into reinforcement learning agents on Atari games here. And what you can see is that using pure neurosymbolic perfectly trained policy and then swapping from the perfect information to our raw image detector without using any hack, without using Kalman filter or anything that would stabilize a bit, we were able to still have way better performance than the original one. So still, like, that was a bit brittle, but down the line, it's going to be just engineering to get these to be as good as deep learners. And they are using object-centric representation. So ultimately, we could use the nudge framework that we developed with Hikaru. And on the same project, what we've been using with Hiki in the paper is this OC-Atari framework that is giving you object-centric representation of these Atari games. So if you don't want to go into optimizing a neural network to detect these objects, you can directly use OC-Atari. This is something that we've developed because it was needed. If we want to push neurosymbolic agent, we both need the alpha ILP framework that is really nice to be integrated in reinforcement learning methods already. but also like object detection stuff. And as reinforcement learning has mainly been concerned, or deep reinforcement learning with these Atari games, we are developing this platform where you obtain an object-centric representation, pretty much like you obtain in the examples that we have with Hikaru.
So, so with this module to recognize what's going on in the game,
yeah.
Are you pre-training that module on runs of the game and then using that to recognize objects in the deep reinforcement learning, or are you training the object recognition concurrently with the policy training?
So far what we've done is that we have used perfect information from this information on where is which object is reconstructed from the RAM, basically. And if I go back to this one, when we trained with reinforcement learning, it was using the perfect information at the beginning, and then we just swapped. So we didn't fine tune. But as you said, it would be way more interesting to train both at the same time. Also, because that way you would be able to understand, for example, that non-moving objects are still objects, like walls and stuff like that, because you would be interacting with the environment. Reinforcement learning would give you this opportunity. And this is all future work. But so far, that's I think the second option you said, like the first option. We first train the reinforcement learning policy and the object detection stuff separately, and we didn't train both at the same time. But the nice thing about this framework is that we train unsupervisedly the object recognition. So you don't have to be any, yeah. So we can just like sample some image from the game using a random policy, and then like use them in order to recognize object already, and use this object recognition system and integrate that in Nudge, for example. We have been integrating Nudge with Atari games also lately.
No, that's really cool.
Okay. So after I'm performing this neurally guided symbolic abstraction, we perform weight optimization. As Quentin said, like prioritize which rule is important to solve the problem. And we use the actor critic framework to update weight rules. So by iterating this process, important rules will get higher values, and not important rules are getting low values. And in the end, we have a policy function as a set of weighted rules, and only important rules will have high weights, large weights. And yeah, that's how we compose the policy reasoning and the policy learning in general. And yeah, for experiments, Quentin can take over. Yeah.
Yeah. Unless Paulo, you have any question on the rest, or but otherwise we could speak about like how we design the experiments.
Yeah, let's talk about the experiments.
All right. So the main experiments that we have, because we just added some experiments on some Atari games already, but there are some limitations that would need further work to be pushed for more Atari games. But the experiments that we have are mainly based on 3 environments, where we also have developed variations of these environments to show what Neurosymbolic is capable of compared to deep approaches. The first environment that we used was Get Out. So that's the environment that was a bit the example that we had through the presentation. In this environment, the first one, you have an agent that is supposed to get a key, collect a key, then go to the door while avoiding an enemy. And we have a Get Out plus variation where you have multiple enemies. Lately, we've been able to, and that's what you're going to see normally in the animation, in the evaluation that we're going to show. We have some small video of the agent playing. We have, I think, up to 5 enemies, even if we learn with only 1 enemy. The second environment is the big fish environment, where you're playing this pink agent, and your goal is to eat the smaller fishes and dodge the bigger fishes. So the bigger fish are going to eat you, and the small fish are the one you want to eat. The more you do that, the more you grow. until at some point you're the biggest possible fish, and then you've won the game basically. And we made a variation that is based on color. So this time you don't have to eat a bigger fish because they are approximately, I think, all the same size. But you have to eat the green fish that are good fish that are eatable, and the red ones are poisonous, so are the ones that you would like to dodge. And the last environment that we have is this heist environment where you're trying to get the key and then go to the lock. So it's a bit like a taxi environment where you're trying to collect a passenger and then deliver it, would be the same idea. And so what you have to do here is to go collect the key and then open the chests. And we have two variations. We have one where you have more chests, because in the original environment you have 1 to 2 chests, and we also have a color variation. And so if we go to the results, here you can see like different approaches. First, we have our baseline, that is the neural PPO agent that is used to find performance, but also for finding like which rule is a good rule or not. So we use the neural guidance from this PPO critic in order to find a suitable set of rule. And then we compare different nudge agents where we refine all the time the set of rules that we have. So we discard rules that were pre-selected. And the purple one is also an expert supervision. So that means that the expert has selected the suitable rules from the beginning. So a human said, okay, those are promising rules that I would keep in order to play. So that's pretty nice, because that allows to have human in the loop. And we know that only these rules are going to be taken into account in order to make the final evaluation. Of course, it's a limitation, because if the expert didn't think about a rule that is a promising rule, then you're not going to have that in your policy. But yeah, I think we incorporated the correct rules, because at least for the fish environment, you can see that this is even the best performing policy. Yeah.
One moment, please. Ruffy.
Nice.
Nice. Yeah.
Very nice.
That's a good idea.
Yeah.
If I still have to have a bit. But yeah, and so here what you can see is that actually we perform in par, if not even better, than the deep environments, than the deep, reinforcement learning agents that use neural networks. So the Neuro Symbolic approach actually are pretty competitive. These three environments show that the Neuro Symbolic, and so the explainability is not impacting the performance. But of course, all these environments have some common characteristic that you don't have in the general world, that we're going to come in the I'm going to come to that in the limitation towards the end, that we need a bit more work in order to for our Neuro Symbolic agent to be as good as every deep agent in the general world. But they show advantages that we have.
And what is the top KRF, and what does ES mean on this chart?
So ES was like the expert supervision. So that's when the human actually crafted the rule. So this rule that you saw, that like jump if the enemy is close by, that's human crafted. So that's for us to have some kind of a per bond maybe, because that would be like if nudge is able to find the perfect rule, or that would be the same as expert. But I say, like, if the expert is bad, maybe there are some rules that are going to be discovered. We haven't found any actually in these environments, but it could be that sometimes, like it happened with the Go game, the AI actually discovered some way of playing that human hadn't thought of. So that would be nice, because you would have interaction in both directions, both from the human to teach the machine, but also the machine teaching the human with interpretable rules nowadays. And the top KRF, Hiki, do you want to comment on that? Because
so we generate a bunch of rules, and we train the weight once, and then some rules get very low weight, almost 0.0, and we basically remove these kind of redundant rules and train again. So top K means like if you say top 10 rules means like using the best 10 rules out of learning and train the weight on top of that again. And that will find, yeah. And we found out that leads to better policies by doing so, yeah. So we have some variant in terms of the number of rules we keep.
Yeah. And so this is why, oh, sorry, Hiki.
No, I'm done.
So this is why you can see that the top 1 rules that are actually the minimum number of rules that you've kept is the fastest learning one, and oftentimes the best performing one, because you only keep the 1 rule that is going to be really important for playing the game.
Yeah,
and
one top K means K rules for each action. Yeah, so top 1 means like we keep 1 rule for each action. So if we have 4 actions, we have 4 rules, action rules in the end, I guess. Yeah.
Okay, so that when you had that other slide that had the right predicate with, you know, right 1 and right 2.
Yes.
Yeah, with top 1, you would have only kept right 1.
Yes, I mean, according to the weight we get after learning, yeah. Okay. Yeah, in this case, right 1 is better. So in the next round, we keep the first rule, for example.
I see.
Because the generator is generating a lot of like different ways of, because the evaluation is not perfect. It gives you a very, very nice heuristic on which rule is promising, but it doesn't really tell you, okay, keep this rule only. And so by evaluating the agent all the time, that allows you to really keep the very nice final rule that is the best one. Yeah. If we go back to the evaluation, so I don't know if you have any other question. We also have like human and random baseline. Yeah. And so then we had we also evaluated our agents on Asterix, the Asterix game and Freeway. And so you can see that we are pretty much on par with the deep approach, I mean, the original approach. And we take DQN here. It's not the most up-to-date, but those games are actually not the most complicated one. In the Atari environment sets, you have like a very diverse set of environment with like very complicated environments that sometimes require other exploration strategies and stuff like that. So we kept like environment that are still solvable by DQN because that's all by actor-critic methods where you don't need complicated exploration strategy, because that's a bit orthogonal to our work. And we still tried on Atari. The only thing is that we need to have environment that have also neurosymbolic representation, which is like what I was showing earlier, what we have been developed also, what we've been developing, sorry. And here, so that's the final performances that we have. And you can see down there like rules that we have rewritten at the end. We have like right going to the key, right going to the door. We rewrote those rules. And if you go in the paper in the appendix, you have for each policy which rule was kept, basically. Yeah, I think we can go to next slide, Hiki.
Did we explain this adaptation to the new
environment? I was going to just ask about that.
Oh yeah. Oh, sorry. That was the colored one. Oh yeah. I thought it was the original one, and it would have been on the next one. Sorry. So that's the adaptation that here. So the color one. So here you can see that we look at like how good nudge and the original neural PPO baseline would perform on the different environments. And for get out plus and the loot color variation, and for the loot plus also, we didn't change anything. So we keep the same final policy. But for the 3 fishes, actually, we wanted to show that you have an easy way, because the rules are interpretable. You have an easy way to interact with the human. And so for the 3 fishes color, what we did is that we just changed the predicate is bigger than in the rule with the predicate is color green. So by just changing this predicate, by taking every rule and saying, okay, we change this predicate to this one now, we were able to change the agent. So in 3 fishes, it's not exactly the same agent that generalized, because obviously would not, but we were able to do that, and we cannot do that on a deep agent. Yeah.
Okay, so that's a really nice result, I think.
Yeah.
It's very easy to adapt new environment with some changes compared to the trained original environment. So that it's pretty cool advantage on the symbolic representation.
Yeah, that's part of the advantage. And on the get out, like you're going to see, actually it understood that if there is an object that is of type enemy that is close by the agent, it has to jump. And so it's going to be able to generalize here. You don't have to tell it like, okay, now you have multiple enemies or something like that. Thing is that we try to see if the neural PPO would be able to manage that. And in our experiment, it was not. So for this one, we didn't change anything. We didn't modify anything from the policy, but the logic nature, the first order logic nature of the alpha LP framework allows to have this generalization. It's pretty neat, actually. So do you want to go to the videos? Like we have some rendering of the agents.
Yeah, let's see it.
So this is the agent that is playing on like so you can see you have like many enemies now, more than before, static and dynamic one. We learn only with a dynamic enemy. And so this is one rendering of one agent, one level basically. And for the GIF not to be too low, too heavy, we just render that. But I think, on the GitHub, you have a way to render the trained agents. We have pushed everything, so shouldn't be very difficult to see how it plays. So, and you can see that we put the reason, like the action that was selected at the top, but it would have made the drawing more complicated, but so you can see it's saying like right to the key, then it goes like left to the door. And so you could look at like what is composing left to the key or right to the key and left to the door. And you could also run the explainability technique to see like what is the most important feature that led to this decision, basically. For the next agent, I think it's the fish one. So the first one on the left is on the original environment. So it's left to it, down to it, etc. So it's always going to the smaller fishes. And what you can see is that sometimes, so on the 4th or 5th, just after this one, it's going to go down and then up and down again, because it wants to go down to actually eat the fish, but it also doesn't want to go down, because at some point, if it goes down more, it's going to die. So right at this moment, it's alternating. Yeah, it's doing this movement. Of course, if we had a planner, we could also just like compute the optimal path, so to say, and instead of going down, then up, then down, then up, we could also go left directly. That was not the focus here. And it's really nice to see that it understood that dodging is more important than going to the fish, because if you miss a fish, it's not bad. Like you just delay your reward. But if you collide on a bigger fish, you're just going to die and it's over and you cannot get any more reward. If we play the next one, that's the environment where we just swapped nicely, just the color. And it just knows that it has to go to the green fish. We didn't have to change anything. Yeah. If you go to the next slide, you have the same rendering on the last environment, the loot environments, where you learn to get the keys and then open the chests. And then like this one, we didn't change anything because one of the predicate was that if you have the key of the chest of the same color, so it learned that like it needs to have the same color. So now if you swap the color, it's just going to compare the color again, and you don't need to change anything. The deep agents didn't understand that somehow. So yeah. Yeah. So, and if we go to a bit of the limitation that like you haven't seen there. Ah, no, there was some more explanation before. Yeah. So the very nice thing about nudge is that you have both this interpretability in the sense that like the agent is really able to, or you're really able to understand the reasoning behind the action decision. Whereas explainability, or in our work, we're not the only one doing this distinction because oftentimes those two terms are used interchangeably. You can use interpretable or explainable, whichever. But there were some people explaining that explainable is interested in like what is important in your input or in the computation that is internally happening for you to take the decision. But it doesn't tell you like why the decision was taken. So in my example that you had on the misalignment problem, that was the heat map. The heat maps tells you the coin is important for getting reward or something, but it doesn't tell you how the coin is going to be considered. And actually it's not. Same here. It's telling you the enemy is important, but it doesn't tell you what is my reasoning on the enemy. And if you have a deep agent, you just have to hope that whatever emerge is the correct decision, is the correct policy, but you cannot interpret. And I think even if you start having MLP deep transformers that try to explain what is happening inside a policy, I think it's still not sufficient. We had this discussion lately of if you start having agent that can explain using natural language their behavior, is that going to be enough? I think they can still misalign, and the explanation can be misaligned. So they can tell you like the agent is going to the coin without actually the agent being going to the coin, because it's just like stochastic system. So eventually it's going to make you hear what you want to hear, but you cannot be 100% sure that it's doing the right thing. Whereas with this interpretable approach, with this neurosymbolic approach based on first order logic, you are able to understand that, yeah, okay, it's really going to the key. It's really avoiding jumping to avoid the enemy, etc., etc. And same, like we have this explainability that you can see here on the figure 5. So when the decision right key was taken, we can say, okay, but what is important in the input space for this decision to be taken? And it's going to tell you, okay, for going right to the key, the most important thing is that I don't have the key, that the key is on the right side. And like this is what you see, these are the blue, dark blue stuff. Whereas if I asked, if you had to jump, why would you have jumped? It would tell you because the object 1 and object 4 would have been very close by. And here the object 1 would have been an agent and the object 4 an enemy in this example. Yeah, I don't know if you have any question on interpretability versus explainability or.
No, that's actually quite clear.
Nice.
You know, one thing that wanted to ask you guys about in terms of, you know, future work, you know, being that you have a agent policy expressed as a set of rules, why not like build in hierarchical, you know, structure in there within your rules? Like I could imagine having higher level goals being expressed in the logic and stuff like that.
This is exactly like one of the things we want to tackle just after. Actually, I think that's one, if not the most pressing one that we would like to have, like hierarchical reinforcement learning based on this logic. We have found like different things we would like to tackle. And so maybe here you can go to the next slide, because that's like here we explain like what what we did, but yeah, the three main thing that we wanted to have, no problem, for future work, were actually, we would like also to have attention, because one of the problem you might have is that in the real world, you also have like many different fishes, for example, that are in the lake. So you might want to actually, like, logic will not easily be able to handle like 50 enemies or something, or these rules. I mean, they can handle that, but we think that it would require attention in order to be sure on which neurosymbolic object you want to concentrate on. And so we were thinking that like implementing some kind of attention somewhere would really help tackling environments where you have like many more object and different object types, because this attention mechanism eventually is going to tell you, okay, like this is what you want to concentrate on at the moment in this specific state. But what you just mentioned, like the high level action, is exactly that. Is this hierarchical RL? Like we would like to, instead of saying go right, go up, we would like to have like this action that is like go to the fish, and then this action would be composed of like sub actions basically. And this is when you have hierarchical RL. Now, one of the question would be, in my opinion, something very interesting to discuss is that is it very interesting to have logic all the way down the line, or neurosymbolic first order logic all the way down the line, or should we have this logic planner that is at the high level actions and let deep solver somehow, or pre-program solver solve these actions? These I don't know. I think many approaches are going to emerge, and that's going to be exciting.
Actually, we can even implement the planner using our differentiable logic. I mean, if you Google like Prolog planner or something, you get a bunch of code to implement planner on a Prolog, and if we write a code using our differentiable language, internally we can have a planner which is still differentiable. And that might be one approach. Actually, we have discussed these approaches for other work with colleagues a lot, and I think it's pretty promising to have a planner, to implement planner inside of a language, and that could help to solve this situation. But yeah, in general, like hierarchical approaches, definitely we should go.
Yeah, I can totally see why. And I think that's also a fair point on kind of, where do you, how low of a level do you want the logic to go? And I think in things like robotics, that I think plays a big role, is your goal to train down to the level of the actuator, or is your goal to make something portable and assume all that low level stuff is just taken care of?
Yeah, I'm more going for the second type of approach, also because that way you can generalize what you've learned. Yeah, I mean, I think humans, they use logic at a certain level, and I think already, like, there are some stuff that we intuitively understand that are not really even logic based. And oftentimes I think that we use logic as an explanation a posteriori to justify what we did. But this logic reasoner that we have incorporated in our mind is sparsely triggered, so to say. I mean, for complicated tasks, it is necessary to use logic. And if we don't use logic, or neurosymbolic approaches, we might end up actually be misaligned. But as you say, like when I'm grasping my cup now, like all the actuator movement, nobody needs an explanation for how I solve that actually. And I think these could be still given to deep reinforcement learning approaches. And you could like trigger these by having this logic planner that is pretty high level. That makes very complicated system after that, but it's super interesting.
All right, well, I want to thank you both for taking the time today. I think this video is going to be of interest to a lot of people. And, thanks again for everyone tuning in.